Welcome to this explainer. When we look at modern, ultra-efficient structures, they definitely don't just happen by accident. There's this massive hidden layer of complex science and technology working behind the scenes to ensure they operate perfectly within their environment. If you've ever wondered how on earth a skyscraper manages to stay completely cool under a blazing summer sun without totally bankrupting its owners, or how a passive house stays perfectly comfortable in the dead of winter, the secret really boils down to computational physics. So today, we're going to unpack exactly how we design the sustainable buildings of the future and look at the specific mechanics that make it all possible. Okay, let's dive right into this. How do you actually test a building's energy before a single brick is laid? It sounds a bit like a paradox, doesn't it? But think about the incredibly high stakes involved in commercial and residential construction. We're talking about massive investments of capital, steel, concrete, and labor going into a structure that's expected to stand and operate efficiently for 50, maybe even 100 years. If you actually wait until the building is completely finished to see if your heating or cooling systems do their job, well, you're way too late. To avoid what could easily become a multi-million-dollar disaster, we absolutely need a virtual test drive. We need a rigorous way to push a building's energy systems to their absolute limits, while the entire project is literally just an idea on a computer screen. And to pull off that virtual test drive, there's really just one important number you need to keep in mind, and that's 1. While there are countless architectural tools out there for drawing and drafting, there is really just one core, foundational, industry-standard engine capable of solving this highly complex thermodynamic challenge. It's the absolute gold standard for predicting building behavior. This single tool basically replaces entire rooms full of engineers doing static math, and it transforms an architect's aesthetic vision into a mathematically sound, deeply energy-efficient reality. Today, we're pulling back the curtain on this singular engine.
Here is our roadmap for today. We'll start with the building energy problem, move into what thermal simulation actually is, introduce the EnergyPlus software, break down how the simulation works, and then wrap up with why this matters today. Let's get right into it.
Section 1. The building energy problem. Buildings actually account for nearly 40% of global energy consumption, so understanding exactly what goes wrong when they aren't optimized is our crucial first step. Let's compare the blindly built approach with the simulated and optimized approach. When you build blind, it's what happens when you build without any real foresight. You inevitably end up with totally unknown operational costs and massive energy waste. In these scenarios, designers might just ignore things like thermal bridging, which is where heat literally bypasses your insulation through highly conductive materials like steel framing, or they might just have poor solar orientation, completely baking the building in the summer sun. You're essentially crossing your fingers and hoping for the best. But contrast that with an optimized approach. It's predictable, it's highly efficient, and it's carefully planned. An optimized building factors in those exact thermal bridges and passive solar gains way before construction starts. A blindly built structure just leaks money and harms the environment every single day it operates, which really cements exactly why shifting to a mathematically simulated approach is totally non-negotiable today. Section 2. What is thermal simulation? We know the problem, so let's go ahead and demystify the solution. Now, what's really fascinating here is that building thermal simulation is, at its core, a virtual test drive of a building's energy systems and climate response prior to construction. Think about how profound that actually is. We're taking abstract environmental physics, things like sunlight angles, wind patterns, humidity, and temperature fluctuations, and turning them into a tangible digital testing environment. You're essentially placing a high-fidelity digital twin of your building into a digital version of its specific future environment to see exactly how its materials and systems will react, long before the foundation is ever poured. Ultimately, this whole process is all about predicting the future. Thermal simulation demands foresight and totally eliminates guesswork from the architectural process. By predicting a building's future energy use, engineers can make incredibly specific adjustments. Like, for example, they can simulate exactly what happens if they swap double pane glass for triple pane glass on a south-facing facade. They can instantly see if the upfront cost of that better glass is going to pay for itself in reduced air conditioning loads over the next 10 years. It takes the somewhat abstract concept of energy efficiency and makes it completely tangible and actionable. Section 3. Introducing EnergyPlus software. Let's zero in on the specific, industry-leading tool that makes all this conceptual simulation a reality. In the past, traditional design relied really heavily on estimating and, well, educated guessing. Engineers had to use static, worst-case scenario calculations that just couldn't account for the dynamic, minute-by-minute weather changes over a full year. But EnergyPlus? It completely changes the paradigm. It's a precision, data-driven engine. It simply doesn't guess. It uses sub-hourly time steps to calculate the exact radiant heat exchange, thermal mass impacts, and moisture transfer inside the building. It crunches these vast amounts of complex thermal equations to give design teams exact performance metrics, which fundamentally revolutionizes the reliability of building design.
Section 4. How the simulation works. So, how exactly do we know if a design works before we build it? Let's move through this and see how it builds, because it's kind of like a mini narrative of digital transformation. Step 1, you input exact weather data. We're talking historical and projected files detailing the exact sun, wind, and temperature for the building's specific geographic coordinates. Step 2, you define the building geometry. And this isn't just the shape, it's the specific thermal properties of the windows, the concrete, the insulation. Step 3, set your HVAC inputs, the systems that will actually keep people comfortable inside. And finally, step 4, you run the simulation. You take all that raw, isolated data, feed it right into the physics engine, and let it calculate the interplay of every single variable. And this brilliantly illustrates what happens under the hood. The engine meticulously analyzes how the structural geometry interacts directly with the path of the sun. For instance, it figures out exactly how the morning light hitting a glass lobby will alter the required HVAC load, testing to see if the cooling systems will end up overworking or underperforming at that specific hour. It does this by evaluating the HVAC systems against that dynamic local climate data, running these complex calculations for every single hour or even fractions of an hour for a full 365-day cycle. The final output is a highly optimized set of performance metrics, proving the design will actually work under real-world conditions. Section 5. Why this matters today. Let's zoom back out from the technical mechanics of the software and connect this right back to our macro world. Because at the end of the day, the ultimate goal of utilizing building thermal simulation with EnergyPlus is saving energy, saving money, and protecting the environment through precision design. By ensuring our buildings are as efficient as mathematically possible before we even break ground, we're drastically reducing our carbon footprint. And when you scale that up from a single building to an entire urban grid, the impact is absolutely staggering. We're transitioning from wasteful, reactive construction to a built environment that works intelligently in harmony with nature, rather than constantly fighting against it just to maintain a livable temperature. So, what does the energy-optimized future of your built environment look like? Next time you walk past a massive construction site or you're just sitting in a perfectly climate-controlled office space, I want you to think about the invisible data, the virtual test drives, and the sub-hourly simulations that made it all possible. The sustainable future of our cities is being decided right now through computational physics, and it is a future built on absolute precision. Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you next time.